Hey everyone, welcome to week 6.
This week, we will cover error in epidemiological studies, so things that can go wrong. The first category of errors we'll discuss is bias, and the second is confounding. By the end of this module, you should be able to identify bias and confounding, understand how these errors impact study results, and know methods of minimizing bias and confounding. And let's start by talking a little bit about bias. As I've mentioned, bias is a type of error. It can happen when selecting participants to be in the study, as is the case of selection bias. And what happens here is that the participants who are selected or who volunteer don't represent the source population. That's the population the researchers want to generalize their study results back to. Bias can also occur when investigators are collecting information, as is the case of information bias. Information bias happens when the information that investigators collect from study participants is not accurate. Bias can be differential or non-differential. Differential is the most dangerous because it happens differently for each study group or each comparison group in the study. For example, it happens differently for the exposed versus the unexposed, or differently for cases versus controls. Non-differential bias happens the same way for each study or comparison group, and because it happens the same way for each group, it is not as threatening to the study results. Selection bias can happen not only when selecting participants, but retaining them, as in the case of follow-up studies where you need to contact participants over and over again. If the people who are selected or retained are systematically different than the source population, then you have selection bias. For example, maybe the people who volunteer to be part of the study or who decide to stay in the study, if it's a follow-up study, are more health conscious. Maybe they engage in healthier behaviors. And so you conduct your study in a population of healthier people, of more health conscious people, and the study results are then not generalizable back to that larger source population, which is composed of people who are health conscious and not. This results in low external validity, meaning that the study results are not true for the source population. Information bias, on the other hand, can only happen when the investigators are collecting information from study participants. The consequence of collecting inaccurate information is misclassification. That means participants are put into the wrong cells in a 2x2 table. So maybe they're classified as exposed when they're not, or maybe they're classified as having the outcome when they don't. When misclassification occurs, the result that is then calculated from that 2x2 table is inaccurate. So if you're calculating risks and risk ratios, they are wrong. And this means that your internal validity is low. The results are not true for the people in the study. And if the results aren't true for the people in the study, they're also not true for the people outside of the study. So you can't have external validity without first having internal validity. There are several ways that investigators can minimize or eliminate bias. Regarding selection bias, investigators can use random sampling methods so that they recruit a random assortment of people from that source population. So the study population is then representative of the source population, and they can work on retaining participants who have already agreed to be in the study over a follow-up period, perhaps by initiating more frequent contact. So getting in touch every year instead of every 3 years. With regard to minimizing information bias, investigators can use validated methods and instruments to collect data. They can double-check data that they've collected using secondary sources, and they can train interviewers to be consistent, whether the interviewer is interviewing a case or control or an exposed or unexposed person. The second type of error we'll discuss this week is confounding. Confounding happens when a third variable, called a confounder, distorts the association between the exposure and outcome. The consequence is that the study result will be incorrect. We say that it is confounded by a third variable. Confounding can be minimized by employing strategies during the design or analysis phases of the study. In order for a variable to qualify as a confounder, it must meet these 3 criteria. So if you're wondering, is this third variable a confounder of the exposure-outcome relationship, ask yourself whether it meets these 3 criteria. If it does, it could potentially be a confounder. When investigators identify potential confounders before they conduct the study, they can implement some methods in the design phase to try to minimize or control for confounding. And these are randomization if the study is experimental, restrictions, so selecting people to be in the study who are only in one category of that confounding variable. So if they think sex is a confounder, maybe they choose only males to be in the study. And the last is matching, so recruiting a person in one comparison group that is like the person in the other comparison group with respect to a confounder. So if they recruit a smoker into the exposure group, they would recruit a smoker into the non-exposed group. If investigators decide not to control for confounding in the design phase, they might collect data on that confounder during the data collection phase, and then control for it in the analysis phase. And they can do this by standardization. This is usually age standardization, which we're actually not going to cover in this class because it is not used all that often for analytic studies. The second is stratification, so analyzing the data separately for categories of the confounder. So if sex is a confounder, analyzing the data separately for males and females. And the last is statistical adjustments, so running multivariate regression models where confounders are statistically controlled for. Stratification, that second method of controlling for confounding in the analysis phase, can be used not only to control for, but also identify whether a variable is a confounder of the exposure-outcome relationship. And we do this by going through the steps listed here. The first step is to stratify by the potential confounder. So this means creating separate 2x2 tables for each category of the confounder. In this case, if we think that smoking is a confounder of the relationship between carrying matches and lung cancer, we would look at that exposure-outcome relationship separately for smokers and non-smokers. The second step is to calculate a measure of association for each 2x2 table. So for the overall data, this is called the crude association, and for the categories of the confounder, these are called stratum-specific associations. So if this is a cohort study, then risk or rate ratio would be the appropriate measure of association to calculate, and we would calculate that for each table. The third and final step is comparing these measures of association. So we start by first comparing the stratum-specific associations to each other, and we see that they are similar, meaning they are within 10% of each other. If the stratum-specific associations are similar to each other, but different from the crude association, that is more than 10% different, we can say the variable is a confounder. So in this case, smoking is a confounder of the relationship between carrying matches and lung cancer. It actually explains why we see this relationship between carrying matches and lung cancer. And so when we remove that effect through stratification, we no longer see a relationship between carrying matches and lung cancer. The reason I say we no longer see a relationship is because the stratum-specific estimates, so those for smokers and non-smokers, are approximately 1, and 1 is the null value for a risk ratio or a rate ratio. 1 means no association. So to recap, this week we will talk about bias and confounding, which are errors in epidemiological studies that lead to false study results. We're doing this because understanding how these errors occur will help you assess the validity, the accuracy of studies that you see published in scientific journals or in the news. All of these concepts will be explained in a more in-depth way in the assigned readings and videos for this week, but if you end up having any questions, please feel free to reach out. Bye, everyone!